So, good morning all of you. After a long gap, we're again starting a VLSI technology course, and today we'll discuss on a new topic, and that topic is epitaxy. Epitaxy is an important topic in VLSI technology, particularly in bipolar ICs. But nowadays in CMOS also epitaxy step is being used widely because of certain advantage, and that advantage is latch-up prevention. But in bipolar VLSI technology, bipolar VLSI process, epitaxy is must, because you want to isolate one device from other. So, in order to have isolation, so you have to have epitaxial layer, so that you can create islands of semiconductor single crystal layer in which you can fabricate devices which are isolated from each other. That means you can create isolated islands. So, for that you have to have epitaxial layer, and epitaxy is a ordered growth of single crystal silicon, and the purity and uniformity of growth is very important in epitaxial process. The word epitaxy comes from two words. One is known as epi. Epi means upon, and another word is taxis. Taxis means order. That means order growth of a monocrystalline layer that bears a definite relation to the underlying monocrystalline substrate. Many of the naturally occurring crystals are formed by this method. Purity and crystal quality of epi layer is better than in substrate. That means we take lot of precautions, lot of care, so that the thin film of monocrystal layer is highly pure. At the same time, it is free from crystallographic defects. Silicon epitaxy is used for bipolar devices, and in CMOS epitaxy is used mainly for latch-up prevention. In compound semiconductor technology, epitaxy is a widely employed process in order to achieve the compound semiconductor films, for example gallium arsenide or indium arsenide or gallium phosphide or ternary material gallium aluminum arsenide, etc. In case of bipolar ICs, for high speed applications, means high speed digital circuits, 1 to 3 micron epi layer is used, but for linear circuits the thickness of the epi layer is of the order of 3 to 10 micron. But at present VLSI technology, sometimes people are using epitaxial film which is less than micron. Now, a feature of the epitaxy is that the doping of the epitaxial layer is relatively independent of the substrate doping. That is one important feature. And now we classify the epitaxial techniques. There are 4 epitaxial classifications. Those are known as homoepitaxy, pseudo-homoepitaxy, heteroepitaxy, and pseudo-heteroepitaxy. Now, let us discuss little bit in detail on these classifications. In homoepitaxy, the epitaxial film and the substrate are of the same material. That means if we make epitaxial film A on a substrate A stands for a particular material, then this is known as homoepitaxy. Example is silicon on silicon. That means substrate material and epitaxial film material are same. Another is gallium arsenide on gallium arsenide, or zinc sulfide on zinc sulfide. So these are all known as homoepitaxy. Second class is pseudo homoepitaxy, and in this particular class epi film and substrate are of same composition, but doping in epi layer can be different from that of substrate. Means we are making a film A on substrate A, but the doping level of the film may be different from that of the substrate. That means A to power B on A, B is the doping impurity and A is the film, epitaxial film, and substrate is also A. Similarly, you can form A substrate, A film of doping B on A substrate of doping C. Substrate is different concentration, that is C doping, and film is another concentration doping, impurity doping, that is B. Or also you can make doped silicon film on undoped silicon substrate. That means in this particular class pseudo homoepitaxy is basically an epitaxial homoepitaxial method, but only difference is that doping impurity may be different. Third category is heteroepitaxy. In this category, dissimilar epi film and substrate materials are used. That means substrate is of material A, but epitaxial film on material is of material B. B on A. Okay. Examples are here. You see, germanium on silicon. Silicon is the substrate, germanium is the epitaxial film. You see, epitaxial film and substrate are not only differ in impurity concentration, but also material itself differ. Okay. Another is gallium phosphide on silicon, silicon on sapphire. Sapphire is alumina, Al2O3. Substrate is sapphire. On sapphire you are growing silicon crystal, that is totally different material, that is heteroepitaxy. Another is SOI, silicon on insulator. The substrate is on insulator and silicon you are growing on that. Okay. And the last category is pseudo heteroepitaxy. Here again chemical commonality between film and substrate is there, but materials are different. Here this class is not similar to pseudo homoepitaxy. Here you see, example is gallium phosphide and gallium antimonide. Two are different material, but one commonality is there, in both the composition gallium is there. So that's why gallium phosphide on gallium antimonide or gallium arsenide is an example of pseudo heteroepitaxy. So out of these four classifications, popular use is which one? Pseudo homoepitaxy, because their substrate and epitaxial film must be of same material, but a different chemical composition, different impurity composition. Okay, that is of practical use. And nowadays heteroepitaxy is another area which is being used widely recently, last 10 years approximately, that is silicon on germanium, silicon germanium material. So that is another area, heteroepitaxy. And 3-5 semiconductor also, we grow heterojunction devices, there you need heteroepitaxial film. So those two, silicon germanium or the 3-5 semiconductor materials where you can grow heteroepitaxy and which will form heterojunction devices, and those devices may be used for high speed circuits particularly. Now next I will discuss on epitaxy techniques. What are the various techniques by which we grow epitaxy? And broadly those techniques are four. One is known as vapor phase epitaxy, which is abbreviated as VPE. Then it will come liquid phase epitaxy, LPE. Then comes solid phase epitaxy, SPE. Then come molecular beam epitaxy, MBE. So, these are broad 4 categories, and we will discuss one categories in detail. First, let us talk on vapor phase epitaxy or VPE. What is vapor phase epitaxy? So, there materials of epitaxial film are transported in the form of vapor, either of the elements or of its compounds. The material transport is in the form of vapor, and that vapor may be in the form of element or of its compound. Element itself, that means which you are going to make the film, that may be in the vapor form, or you can use its compound, which at high temperature decomposes and give the element or the material whose film you want to make. Okay. Now, the second one, VP point, VP is a very popular technique because of its wide flexibility in terms of process parameter control, chemical system choices, process scaling, and related process adaptability. That is why VP is highly used in commercial purpose also. It is highly flexible. Flexibility in terms of process parameter control, flexibility in terms of chemical system choices, flexibility in terms of process scaling, and process adaptability. These are few advantages of VP, and we use VP in bipolar VLSI process very much. Now, there are different VP processes, namely chemical vapor deposition CVD, ultra high vacuum chemical vapor deposition, which is known as UHV CVD, rapid thermal chemical vapor deposition known as RT CVD, molecular beam epitaxy MBE, here the spelling is wrong, BAM, molecular beam epitaxy, and the molecular beam epitaxy may be gas phase, metal organic MBE. So, those techniques CVD, UHV CVD, RT CVD, MBE we will discuss in detail in subsequent classes. And another is organometallic VP, or known as OM VP or MOCVD. Organometallic VP is OM VP, MOCVD is metallo-organic chemical vapor deposition. You can see here all are deposition techniques. Here epitaxy is another name you can get, deposition. You are depositing the film, happens to be the film is single crystal in nature, and if this film is not in single crystal nature, then it will be amorphous or polycrystalline. Amorphous is the metal deposition, is another amorphous. Sputtering deposition of films, maybe dielectric films or the semiconducting films or metal film, those are again deposition, but they are known as sputtered deposition film, deposited film. But when you talk about epitaxy, so then the film which you are going to deposit on substrate, so that film must be of the same crystalline quality on which you are making the film or the substrate, in particular in case of homoepitaxy or pseudo homoepitaxy. Okay. Now, again the VP process must be low DT process, low DT process. That means that D stands for diffusion coefficient, which is a function of temperature, and small t is the time. You know, in a VLSI, the DT product should be as low as possible to prevent redistribution of impurity in the bulk of silicon substrate. In the bulk of the layer in which you are making devices, their redistribution has to be prevented, so that it will not occupy much silicon bulk area and you can get higher density of the films. That is one aim of all processes. which must lead to low DT. So now in epitaxial process, there are two methods by which you can reduce the DT product. One method is let the temperature high, means capital D will be high, but time is too small. Then again DT product will be small. And another maybe the temperature is small, that means diffusion coefficient is small, and small t its time is very high. So both are used in epitaxial techniques in VPE process. And low DT process example is a rapid thermal or limited reaction processing. That is one example of low DT process where time is very small but temperature is high. So that is rapid thermal processing. I have already discussed in ion implantation class. And another low DT process is the plasma or remote plasma or photo or laser CVD, which is known as LCVD or PCVD, photo CVD or laser CVD, and ion beam assisted deposition, which is IBAD, and also sputter. So these are all low DT process. That means there time is more but temperature is less, so diffusion coefficient also very small. Either in plasma CVD or photo CVD or laser CVD or ion beam assisted deposition technique, everywhere you will find temperature doesn't go more than 400 to 500 degrees centigrade maximum. Okay. Whereas in rapid thermal, temperature may go up to 1000 degrees centigrade, but times are very small. So these are the low DT process techniques, and all these techniques are used nowadays in different applications. Now, what is liquid phase epitaxy, LPE? LPE involves growth of epitaxial layers on crystalline substrate by direct precipitation from the liquid phase. That means here the precursor material is in liquid form. In VP, precursors are all in gaseous form. In LP, it is in liquid form. And this particular process, LP process, is popular in compound semiconductor technology. It is not so much popular in silicon technology. The reason of using LP is that in some cases, some of the semiconductor films, the precursors in gaseous form are not available. And again, if it is available, the handling of those precursors are not very simple and easy. So in those cases, liquid precursors, liquid sources are used, and handling is also easy, not difficult, and LP is popular in those cases. In earlier days, compound semiconductor films are mostly grown using the liquid phase epitaxial technique, and that is not very high temperature process, is a room temperature process almost, and sometimes temperature may be higher, but the precursors are not dangerous gases and user friendly gases mostly. So that's why LP is popular in those cases in compound semiconductor area. And another is SPE, solid phase epitaxy. And in solid phase epitaxy, it describes the situation where an amorphous layer of a semiconductor recrystallizes epitaxially on a single crystal substrate at temperature below the melting or eutectic point of the relevant materials. That means in SP, basically the amorphous layer is going to change into single crystal layer in solid phase epitaxial process. And one example is ion implantation followed by annealing. So there, by ion implantation we make amorphous layer, because if you implant impurity atom, the silicon bond structure will disrupt, and the layer will be mostly amorphous layer, and subsequent annealing step will help to recrystallize the single crystal silicon, recrystallize the silicon layer along with incorporation of the impurity dopants. So, that is solid phase epitaxy. Okay. And now we will discuss on categories, general reaction categories of vapor phase epitaxy. Now we will discuss on vapor phase epitaxy in little bit in detail. And there are 4 categories of reactions in vapor phase epitaxy. One is known as hydrogen reduction, and second is known as disproportion reaction, and third is thermal decomposition, and last one is physical evaporation in UHV. So, these are 4 categories reaction mechanisms in vapor phase epitaxy. In this particular case, the precursors are all in vapor form. And the first one is hydrogen reduction equation. There we use SiCl4, which is silicon tetrachloride, and with hydrogen it reduces to silicon and HCl. SiCl4 plus 2H2, it gives silicon plus 4HCl. And the second is disproportionation. So, there we use hydrides of silicon. SiI4 plus silicon gives 2SiI2 at higher temperature, which again decomposes to silicon and SiI4 at a lower temperature. So, this is a 2-step reaction. And last one, third one is thermal decomposition. This is also known as pyrolysis. This thermal decomposition reaction is SiH4, which is silane, is used, and it gives silicon and 2H2O, that is thermal decomposition. It is another name is pyrolysis of silane. And last one is physical evaporation in UHV. In ultra high vacuum, physical evaporation of the material layer by layer in a monolayer basis, and that is known as molecular beam epitaxy or MBE. And here the vacuum level is of the order of 10 to the power minus 10 torr, that is 10 to the power minus 10 millimeter of mercury, is very high vacuum. So, there silicon as a molecule itself you can deposit, that is molecule by molecule it will form a layer, and then another monolayer it will be formed. It is a very slow process, and by this MB process you can grow very thin of the order of say 10 angstrom, 15 angstrom layer of single crystal silicon or other semiconducting materials in 3-5 group. You can prepare using, you can make using MB technique. But out of these 4 techniques, the hydrogen reduction, that is the first one, silicon tetrachloride and hydrogen gives you silicon and HCl, this reaction, and thermal decomposition, that is pyrolysis of silane, the A, C and D are currently used. B is never used nowadays, only for categories sake, division sake I mentioned here, is of no use now. Iodides are not very good composition and its quality is also not good. We use chlorides and hydrides. You see SiCl4 is a chlorides of halogen compounds, and here SiH4 is the hydrides, or sometimes here organometallic compounds are also used. Now, let us see the common source gases of for epitaxial silicon. The source gases for this hydrogen reduction reaction is silicon tetrachloride SiCl4, and the SiCl4 reaction takes place in 1150 to 1250 degrees centigrade, and reaction paths are not direct. 3-step reaction takes place. In the first step, silicon tetrachloride with hydrogen, it gives SiHCl3 plus HCl, and SiHCl3 is trichlorosilane. SiHCl3 is trichlorosilane, and the next step, the trichlorosilane decomposes at this high temperature into SiCl2 plus HCl, and this SiCl2 silicon chloride plus H2 gives you silicon plus 2HCl. So this is the 3-step reaction. And one thing you can see here, that these all the 3 steps are reversible reaction. That means forward direction and as well as backward direction, both direction reaction takes place. So that means, since backward direction reaction is also there, then some of the silicon and HCl, they will combine and they will go back to SiCl4. There is a chance. Okay. And here the precursor gases are silicon tetrachloride and hydrogen. Hydrogen is a carrier gas, and byproduct gases are HCl, and the HCl is, you know, it is also etching gas, and HCl also helps etching silicon, because HCl react with silicon and it will form SiCl4, and SiCl4 is again a gaseous material, silicon tetrachloride. That means the byproduct gas HCl also removes some of the silicon from the surface. Both deposition and etching takes place. But if the forward reaction is more than the backward reaction, then obviously you will get silicon deposition. But if backward reaction is more, then obviously loss of silicon will be there. There is no deposition. Okay. And the second reaction is trichlorosilane, SiHCl3 directly. So you have seen in silicon tetrachloride, it first decomposes to trichlorosilane, then others 2 steps follows. But directly you can use trichlorosilane, which is SiHCl3, and SiHCl3 react with hydrogen at not very high temperature, little bit less temperature compared to SiCl4 reaction, and that temperature is 1100 to 1200 degrees centigrade, and at 11 to 1200 degrees centigrade, the trichlorosilane decomposes to trichlorosilane SiHCl3 decomposes to SiCl2 plus HCl. That means this step directly follows here. Okay. And after the SiCl2, then again another reversible reaction with hydrogen, it makes silicon plus 2HCl. Okay. And next one is SiH2Cl2. This is dichlorosilane. You can use dichlorosilane also. So this SiH2Cl2 reaction takes place 1000 degree to 1100 degree centigrade, and there the reaction is like this. SiH2Cl2 decomposes at high temperature into silicon and to HCl directly, and you are getting HCl byproduct gas. Okay. And the other one, which is pyrolysis reaction, that is hydride you can use, that is SiH4. SiH4 is silane gas, and the silane gas, that reaction takes place at 950 to 1050 degrees centigrade, and it directly decomposes into silicon and hydrogen 2H2. And if you compare all these reactions, then 2 things is very important. 2 things are important. One is, whereas the first, second, third reactions are reversible reaction, the fourth one is irreversible. that is one way reaction. SiH4 changes to Si plus hydrogen. In the second change, you can see compared to the first, second, third reaction is that the reaction byproduct in all the three cases are HCl gas, but in the pyrolysis of silane the reaction byproduct is hydrogen. Hydrogen anyway we are using as a carrier gas, and sometimes we dilute the silane mixing hydrogen with it. So that is why it is not making any harm on the surface, but if the HCl gas is produced, there is a chance of etching of the silicon surface. At the same time, one disadvantage is also there, because before epitaxial growth always silicon surface is cleaned thoroughly by dry etching, and there we use HCl gas. HCl gas you send for some time, some of the silicon layers are etched, and then that means it is known as a cleaning step, and that cleaning step means in situ cleaning is possible in case of the hydrogen reduction equations using whether silicon tetrachloride or dichlorosilane or trichlorosilane, but that in situ cleaning is not possible in case of the silane pyrolysis of hydrides reaction. So these two are important differences among the hydrogen reduction reaction and thermal decomposition of silane reaction. Again, silicon source deposition characteristics are shown here in this table. Silicon tetrachloride temperature 1150 to 1250 degree centigrade, the growth rate is 0.4 to 1.5 micron per minute is the growth rate, and some of the remarks is obviously the temperature of reaction is high, but the reaction is highly stable and good selectivity. These are the three important remarks you can make from silicon tetrachloride reaction. This table basically compares the different reaction mechanism in VPE process, which are not very often used in epitaxial reactors. Silicon tetrachloride is highly stable, good selectivity, but disadvantage is it is a high temperature process, 1150 to 1250 degree centigrade, and you can have considerable growth rate 0.4 micron to 1.5 micron per minute. Trichlorosilane SiHCl3 1100 to 1200 degree centigrade, here the growth rate is 0.4 to 2 micron per minute, higher than the silicon tetrachloride, you can see, and here also temperature is high, but it is easily reduced, that is the disadvantage. In the third one is dichlorosilane SiH2Cl2, here the reaction temperature is 1050 to 1150 degree centigrade, and growth rate is 0.4 to 3 micron, still higher than SiHCl3 reaction, but here temperature is low compared to SiCl4 and trichlorosilane reaction, temperature is 1050 to 1150 degree centigrade. Okay, and is a low T and good quality, low T, low temperature, and quality also good. That is why the dichlorosilane reaction is also popular reaction in VPE process. And the fourth one is SiH4 silane reaction, that is pyrolysis of hydrides of silicon, that is taking place in 950 to 1050 degree centigrade, and here growth rate is little bit low, 0.2 to 0.3 micron per minute. Advantage is low temperature reaction, but disadvantages are there, that is gas phase nucleation deposition problem is there, no in situ HClH, because byproduct is hydrogen not HCl, no in situ HClH. But if you compare this table, then the important feature of the pyrolysis reaction is low temperature. So that is why somebody tells that epitaxial growth by pyrolysis appears to become the most widely applied growth technology in the future. The reactant species for pyrolysis reactions are either hydrides or organometallic compounds, and one of the problem of these hydrides or organometallic compounds are the precursor gases are highly poisonous, very difficult to handle. Silane is much more dangerous chemical compared to silicon tetrachloride. So all hydrides are highly poisonous and difficult to handle compared to silicon tetrachloride. So although the SiH4 people predicts that it will be the epitaxial growth process for the future, but the precautions required for handling the silane is more compared to these chlorides of silicon, means either dichlorosilane or silicon tetrachloride. Even that is why this SiCl4 or SiH2Cl2 is still widely used. Okay. Now, some comparison of the performance of the reactors using different gases are shown here. Since silicon tetrachloride and SiHCl3 are more stable, they can tolerate highest oxidizer contamination. This is another important point. So these two techniques can tolerate highest oxidizer contamination, that means trace of oxygen in the process. The problem is in all these precursor gases, in all techniques, if oxygen contaminations are there either in the carrier gas or in the system, then it will lead to formation of silicon oxide, dioxide, and eventually the crystal quality of the silicon will be very poor, and it may lead to the amorphous nature, that means SiO2 and Si combinations, you may not get perfect single crystal nature of silicon. So that is why the oxygen molecule contamination should be completely avoided, should not be there in the epitaxial reactor process. When that means design also must be critical, gases must be highly pure, no oxygen contamination. Even then we have seen, so these two reaction they can tolerate little bit higher oxygen contamination of the order of 5 to 10 ppm level parts per million. SiH2Cl2 can tolerate less than 5 ppm and SiH4 can tolerate less than 2 ppm. Although these two cases reaction temperature is less compared to the first two cases, even then in consideration to tolerance of oxygen molecules, the last two are not that much good compared to the first two, that means SiCl4 and SiHCl3. Next point is SiH4 decomposition starts at 500 degrees centigrade at very low temperature, but it is enable for in situ silicon etch in SiH4 system, which causes stacking faults. That means in SiH4 system, initially you have to send HCl gases into the chamber to clean the silicon surface, and after that again you have to purge with hydrogen gas, that is removal of all HCl gases, and then you can start flowing SiH4 using the flow meter. Okay. So now this particular step, that means in situ cleaning is not there, that may lead to stacking faults, which is a crystallographic defect. And another problem in SiH4 is gas phase homogeneous nucleation, and that will lead to polycrystalline growth. Gas phase homogeneous nucleation means actually nucleation of silicon should take place on silicon substrate itself, not in the gas phase. But in case of SiH4 reaction, silent reaction, it has been observed that some of the, in the gas phase itself, some of the SiH4 decomposes and silicon nucleation takes place, and those particles of silicon may deposit on the substrate. And the next slide I will show how the reaction takes place, what are the steps of reaction in VP process, so that silicon layer by layer will form on single crystal silicon substrate. So gas phase nucleation is not desirable in any epitaxial system. Now we discuss on VP reactor system, how the VP reactor looks like. So here the schematic diagram of vapor phase epitaxial reactor. So this is the reactor, which is made of quartz, good quality quartz, and since the reaction takes place at a higher temperature in the range of 1200 degrees centigrade for SiCl4 and in the range of 900 degrees centigrade for silent reaction. So some heating arrangements must be there, and there are two types of heating arrangements available. One is known as cold wall heating arrangement, another is hot wall heating arrangement. There are two types of heating arrangement, and cold wall heating arrangements means if we use resistive heating, that means resistance coils are used, and if you send high current through the coils, the heat will be generated and it will heat the chamber. So there the wall of the reactor will be hot, at the same time the substrate and susceptor combination will also be hot, and the substrates are kept on a container which is known as susceptor. You see it is CPTOR is a susceptor, is the container of silicon substrate. And I was talking about the hot wall and cold wall reactors. So if you use the resistive heating, then it is a hot wall reactor. But on the other hand, if you use RF heating, means if you use RF coils, so there the wall will not be heated, rather the susceptor and substrate will be heated. At that particular location, heat will be concentrated. It can be done. So that is cold wall reactor combination. And also you can use radiant heating, and in the radiant heating the wall is cooled using the liquid flow of liquid, low temperature liquid flow, and radiation lamp radiators are used, halogen lamps, which will heat directly the susceptor. Cold wall reactors are preferable compared to hot wall reactors, because in case of hot wall reactor the contamination from the wall chamber may come on the substrate surface, because in a hot wall reactor the wall are higher temperature compared to the substrate and wafer. So that's the reason the contamination, means impurities, can move from high temperature zone to low temperature zone. Mobility will be high at high temperature zone, it can proceed to the low temperature zone. Since the wall temperature is more compared to the susceptor temperature, the impurity may lead to the susceptor, which will deposit on the substrate. That is in case of hot wall reactor. But if the reactors are cold, then the impurity or the contamination flow will be from susceptor to the wall of the reactors, towards the wall of the reactor, hot region to the cold region. So in that case the epitaxial film may be less contaminated or from impurity from the wall, because reactor walls may originate some of the impurity atoms, and those impurity atoms should not reach on the susceptor surface where the substrates are kept for epitaxial deposition. Okay, these are the two reactor configuration, hot wall reactor and cold wall reactor, and how the hot wall reactor and cold wall reactors are designed, that also I mentioned. Now obviously in the reactor system there should be some arrangement for flowing the precursor gases. So there are different precursor gas paths are here. One is the source gas. Source gas here is SiH2Cl2, dichlorosilane, and you may use here SiCl4 or you may use SiH4, whatever it is. This is the path for the source gas path here. And another is a carrier gas, that is hydrogen is used always in carrier gas. You cannot use any neutral gas like nitrogen, etc. You cannot use, because nitrogen will form nitride, oxygen should not be there at all. So it's always hydrogen, and hydrogen will help in the reduction reaction, is the reducing agent, you know. So that's why in all the epitaxial process we use hydrogen as a carrier gas. So that carrier gas path is here, and these other two are dopant gases. One is arsine ASH3, and this is B2H6, a diborane. Okay, so you may have to grow epitaxial film with certain N type or P type dopant. So for that, two dopant gas connections should be there, either arsine for N type silicon and diborane for making P type silicon. So other than the gas source, you can see here two arrangements. Ones are valve and others are mass flow controller. So mass flow controllers are there. You can see the mass flow controllers. So those mass flow controllers basically regulate the flow of gases very accurately. Okay, so those are the purpose of mass flow controller, because that will lead to the partial pressures inside the reaction chamber, and each individual gas path will have a mass flow controller, so that individually you can control the hydrogen flow or the source gas flow or arsine or diborane flow. And these are the valves which can close the path or open the path. And other side, you see the reaction will take place here. So after the reaction there are byproduct gases, and some of the unused gases will also be there. It is not true the all silane or dichlorosilane will be reacted completely and it will form reaction products. So there will be some unreacted gases. So what will you do with those gases? One is HCl and others is maybe traces of silane or silicon tetrachloride. Those gases you cannot directly expose in the environment, because those gases are highly dangerous for health human being. So those gases are sent through a scrubber. This is the scrubber, is the vacuum pump by which you can suction those gases, and those gases are flown on a scrubber, and in the scrubber basically those gases are dissolved in liquid, and their fountains are there, water fountain, and the gases are flown, and the top the showers of waters are thrown on the gases, and then you can dilute those byproduct gases and eject into the environment. In this way we can remove these hazardous gases and the byproduct gases in the environment before you cannot throw it into the ambient without dilution and without this inaction, because you have to inact the gases. Okay, so these are the total reactor configuration, and the next class we will discuss on the reactions and other details of the reactor configuration. Okay.